Imagine a computer that remembers, not just stores data, but truly remembers. That's the power of a recurrent neural network, or RNN. RNNs are a special kind of artificial intelligence. They learn from sequences of data. This means they remember past inputs to understand the present. Think of it like this: when you read a sentence, you don't understand each word in isolation. You need the context of the words that came before. That's what RNNs do. RNNs are changing the way we interact with technology. They power voice assistants like Siri and Google Translate. They help us predict stock prices and understand complex medical data. The possibilities are endless. These networks are different from traditional neural networks. Traditional networks process information in one direction. They lack the memory of RNNs. This makes RNNs ideal for tasks that involve sequences, like language, music, or time series data. They can find patterns and make predictions based on past information. The world is full of sequential data. From the words we speak to the movements we make, everything happens in a sequence. RNNs give us a powerful tool to understand this data and unlock its secrets. Traditional neural networks, also known as feed-forward networks, are like one-way streets. Information flows in one direction from input to output. They process each input independently without any memory of past inputs. Imagine trying to understand a story by reading one word at a time with no recollection of what came before. It wouldn't make much sense. RNNs, on the other hand, are like two-way streets. They have loops that allow information to persist. This gives them a form of memory, allowing them to remember past inputs and use them to influence their current output. Think of it like this: when you read a sentence, you remember the previous words to understand the meaning of the current word. RNNs work in a similar way, using their memory to process sequential data and understand context. This ability to remember makes RNNs much better at handling sequential data than feed-forward networks. They can learn patterns over time and use them to make predictions about future events. RNNs are everywhere in our technology-driven world. They power the voice assistants we talk to every day, like Siri and Alexa. These assistants rely on RNNs to understand our spoken words and respond accordingly. Another prime example is machine translation. Google Translate, for instance, uses RNNs to convert text from one language to another. The network learns the grammatical rules and patterns of both languages to provide accurate translations. But RNNs are not limited to language processing. They are also used in financial forecasting, predicting stock prices and market trends by analyzing historical data. In medical diagnosis, they identify diseases and predict patient outcomes based on medical records. In self-driving cars, they process sensor data to understand the car's surroundings and make driving decisions. These are just a few examples of the many ways RNNs are being used to solve real-world problems. Section 4. RNN Architectures and Benefits. RNNs come in different flavors, each designed for specific tasks. One common architecture is the one-to-many RNN. Imagine showing a single image to the network and getting a full sentence describing it. That's a one-to-many scenario. Then there's the many-to-one RNN, which is like sentiment analysis. You feed it a block of text and it tells you if the overall sentiment is positive, negative, or neutral. And of course, we have the many-to-many RNN, the workhorse of machine translation. It takes a sequence of words in one language and outputs the translated sequence in another. The benefits of using RNNs are vast. Memory, their ability to remember past inputs, allows them to understand context and make better predictions. Accuracy, RNNs can achieve high levels of accuracy in tasks involving sequential data. Versatility, they can be applied to a wide range of problems, from natural language processing to financial forecasting. Section 5. Challenges and the future of RNNs. RNNs are powerful, but they're not without their challenges. One challenge is the vanishing gradient problem. This occurs when the network has difficulty learning long-term dependencies in the data. Imagine trying to remember something that happened a long time ago. It becomes harder as time goes by. Luckily, we have a solution: long short-term memory networks, or LSTMs. LSTMs are a special kind of RNN designed to overcome the vanishing gradient problem. They have a more complex memory structure that allows them to remember information for longer periods. Another challenge is the computational cost of training RNNs. They can require a lot of data and processing power to train effectively. However, advances in hardware and algorithms are constantly improving the efficiency of RNN training. RNNs are a rapidly evolving field with tremendous potential. As researchers continue to develop new architectures and training techniques, we can expect to see even more innovative applications of RNNs in the years to come. They're already changing the world around us, and their impact is only going to grow.